Thank you, everyone. Welcome to our third talk of this session. Paul Ross is going to be talking about magical fire-breathing creatures. By that I mean C extensions, of course. So please join me in welcoming him.
Thank you. This is about Python, and it's about C as well. If there are any Java developers in the audience, I should just warn you that in a few moments I'm going to show you some C pointers on the slide. I don't want you to get too scared, and so you have been warned about the trauma of pointers. Okay, my name is Paul Ross. I work for AHL. If this will change. Just get that. AHL is a hedge fund based in the City of London. It's part of the Man Group. We've been around quite a long time by hedge fund standards. We're a systematic hedge fund, so it's the algorithms that do the trading rather than human judgment. We've got about $20 billion of client funds under management at the moment, and we're active all around the world, 40 countries, in a huge number of markets, pretty much any financial instrument you can imagine, over 400 markets. The algorithms are very hungry and they need feeding. We take in about 2 billion market data points a day. And if you're interested in how we do that, there's a link there to our open source market tick store called Arctic. And kudos to the AHL team that made that. We're quite small, actually. There's only about 125 people, 22 languages. We're very international. And Python. We're all Python. So Python's fabulous for us. So why write in C? Well, here are some reasons that we find it useful. Blinding performance, we'll see how much C compares with Python in a little while. You might want to interface with existing C and C++ libraries. We do that too. You might want leaner resources in Python, particularly if you've got a very large number of small objects. Python can be quite expensive with that. And you might want to flee the guild, because once you're in C code, you're kind of free from that interpreter logic. We don't really use the last reason very much, but the first three are definitely of interest to us. So where are these dragons then? So on the left, we have Python, we know and love. On the right, you have C, and I'm assuming that you kind of are fairly comfortable with C and all that standard library goodness that's been passed down to us through the generations. The problem happens in the middle here. C Python code. You're writing in C, but you have to follow the Python API and the rules and regulations of that. And getting things wrong here can seriously torture your code base. So the idea of this talk is to turn this dragon into this one. A nice, cuddly, paint-by-numbers dragon that won't do you any harm at all. So we're going to have to talk about how we manage memory, because that's one of the most important things, of course, in C. So how does Python do it? Well, we have automatic memory management, and it's done by reference counting. So every time a Python object is created, its reference count is set to 1. When the reference count goes to 0, the object can be deallocated. So when we're writing our C code, we have to kind of respect this concept. So just so that we're sharing the same idea about reference counting, this is how Python works internally. I'm going to run this little bit of code and show you how reference counts work. So first line, we say A equals foo. So conceptually, what's going to happen is a symbol A is going to appear on the stack. That's going to be referencing this Python object in yellow here. The object has a reference count, and it has an address to the actual real string foo. And the reference count is set to 1, because there's only one A pointing at this reference. If I now say B equals A, B appears on the stack, and that's now incremented the reference count, so there's 2 objects pointing at this string foo. If I then say A equals bar, well, Python will dereference that foo, so decrements the reference count down to 1, because there's only B pointing at it now. It will create bar and the Python object to go with it, with a reference count of 1, so we're now in this situation. If I say delete A, what happens is that Python will decrement that reference count to 0. Once it's at 0, it realizes it can remove bar, remove the Python object, and finally A disappears off the stack. So conceptually, that's how reference counting works. When we write our C code, we're going to have to imitate this. So Python does have garbage collection. That's true, but it's really only for resolving cyclic references, and it only applies to containers. And it's not some magic bit of stuff that will just go and fix all the errors you can make, like lost C allocated memory or lost Python objects. Okay, so the rest of the talk is going to be about the three things that I think are really important writing C extensions in Python. Firstly, I'm going to give you a coding pattern that will keep you out of trouble and keep those dragons away, or at least keep the dragons cuddly. The two things that you really have to avoid, if you could keep that in mind when you're writing C extensions, and the three kinds of Python object pointers that you will encounter in writing C code with CPython. Sorry, Java guys, pointers. Okay, let's look at two things to avoid first. Fairly simply, memory leaks and access after deallocation. So if you look in the C world, here's a memory leak. I've allocated a kilobyte of memory with malloc, and then I set the 8th one to the character A, and then I exit the function. And that memory is lost for the duration of that process. It's leaked memory. Never get it back. What I should have done, of course, is call free on that pointer when I finished with it, free the pointer. But what I've done here is I've done an access after deallocation. So I try and print that 8th character, and in C, most of the time this will actually work. In fact, it's undefined, but usually it'll work because freeing, of course, doesn't actually clear that memory. It just returns it to the memory manager. So in the Python world, if you're writing in CPython, here we are, C code, you now hash included python.h, and that gives you access to all of the good APIs that Python has in C. So here I'm going to create an object here called pob, and I'm going to use this Python function, p-bytes from string, hello world, and that's now going to be a Python object with a reference count of 1, of course. Okay? And I can go and print it. But in this case, I'm going to exit the function after that, and that memory has been leaked here. I've created a Python object, and I haven't made any attempt to deallocate it. How to fix that problem? Very simply, it's the equivalent of free, if you like, is I call this PyDecRef on the object, which decrements the reference count, and that allows a CPython to decide if that object can actually be freed if the ref count goes down to 0. But what I could do is I could be naughty and try and print that object after decrefing it, and that also might work. It might just show up as hello world, but like the C example, it's really quite undefined, and we'll see how we can get into serious trouble in a moment with this problem. So what you might think is, okay, I'll be cute, that last print statement, I'll conditionally print it depending on the reference count. So you're going to try and do something like this. I'm going to decrement the reference count. Then I'm going to check this object what its reference count actually is. And if it's still alive, if it's got a ref count greater than 0, I can go ahead and print it. Please don't do this, because when that PyDecRef is called, if the reference count goes down to 0, CPython can do anything with that memory. And it might indeed just put garbage in that memory. So when you go p-object arrow obj ref count, you might actually be reading garbage and comparing it with 0, and it might just work. And then you're going to try and print garbage, and you might get a sig fault for that. So those are the two things you've got to keep in your mind when you're writing C extensions, is memory leaks and access after free. Okay, let's move on to the three kinds of pointer used in CPython. And I'm going to use a terminology that's in all the Python documentation. So you have a pointer, and which of these three types is it? So when you look at your C code and you see a PyObject pointer, you should be able to identify which of these three it is for every pointer in your C code, because there's important differences between how they behave or how you have to treat them. So first one is new references. This is when a PyObject is created. For example, creating a new list. It just gets created, and it's new. Stolen references occur when a Python object is created and assigned. So for example, appending a new object on the end of a list, or inserting something into a list, something like that. So typically they're kind of setters. So stolen references are typically setters. Borrowed references are used when getting a Python object. So they're getter, so accessing a member of the list or something like that. So I find it conceptually a bit difficult, this word borrowed. So if shared references mean more to you, that's fine, because that's really what they are. So these three different pointers are really programming by contract. And these are the contracts that you enter into. Okay. Firstly, if it's a new PyObject, it's your job to deallocate it, or give it to someone else that will deallocate it when it when appropriate. If it's a stolen pointer to a Py object, the thief, whoever the thief is, will deallocate it, so you shouldn't do so yourself. We'll look at examples of this. Borrowed objects, the real owner can deallocate it at any time without telling you, unless you show some interest in it. And I'll show you how to do that in a moment. So let's look at some code, new references. Here I'm going to take 2 C longs, create 2 Python longs from them, and then subtract them using Python code. So here, PA is a new long, that's a new reference. PB is a new long, that's a new reference. Okay? And R, the result, is calling PyNumberSubtract, which is a Python API for subtracting numbers, obviously. And that gives me another new reference. So I've got 3 new references in play now, but 2 of them are really temporary. They belong to me. And I need to decrement them at the bottom there, both PA and PB. But the return value, R, I leave to the caller to decrement that reference. Okay? And that is a contract that the caller has with this function. Okay? The return value they get, they have to deallocate. So I'm sure you're all C ninjas, and you might say, well, this is a lot of code just to subtract 2 numbers, and you might be very tempted to do it in one line, like this. Okay, so here I'm creating 2 longs, passing them straight into PyNumberSubtract, and I've got 2 leaks now, because PyNumberSubtract has no idea that the pointers you're giving it have to be decremented. That was your job, and you failed. So you've got small leaks, but they're there. Moving on to stolen references. Okay. Stolen references are like setters. So here I'm going to create a tuple of 3 items, and I'm going to put the values 1, 2, and 3 in. So I create R, which is my return value, make a new tuple of 3 items. That's a new reference. That's OK. I'm going to use V to create a long from a long again, and I'm going to set it PyTupleSetItem, give it the tuple, the position, and V, and that now, the tuple now assumes responsibility for that pointer V. Okay, it's stolen that pointer V. Okay, I can reuse a V in this case for creating number 2, set that in position 1, and so on. The more common pattern with stolen references is down the bottom, the line before the return statement, is you create it and set it at the same time, because the tuple is going to take care of deallocation. Okay, please don't do this. For stolen references, here I've used PyTupleSetItem to set V, and then I've gone and decremented V myself. This is going to lead to all sorts of nastiness, okay, because actually the tuple is responsible for doing that rather than you. So, borrowed references. Okay, these are generally getters. So here's an example of we got some list somewhere. Okay, I want to pull out the value, in fact, the 0th item of the list, and I say p-val equals PyListGetItem. Now, the situation we have here is conceptually like this. We've got a list which has foobar baz or whatever, and obviously that has references to all of the objects in the list. And it's now given me, that get item has given me another pointer to the first item. So we've got multiple pointers to the same object. The question arises then, who's responsible for deallocating this object? And what happens to the other pointers when one of them deallocates the pointer? And this can be the source of the most subtle bugs, and I will show you exactly what can go wrong. So here's a function. I'm going to pass in a list, declare a pointer to a P object, and say getItem, get me the 0th element of the list. So now P first is pointing to the 0th element of the list. I'm going to call some other C function on the list. Okay? We don't quite know what that's going to do yet. Okay? And then we're just going to print out the first element of the list. Okay? And then we're going to return none. So nothing can really go wrong here, can it? Well, let's suppose that this function removed the first item in the list. What is my P first pointer now going to say? Well, going to be? Well, okay, let's code this up and kick off the interpreter and find out. Here we're on the interpreter, we import the module, create a list, foobar baz, call this function, borrow bad, and kaboom, on this Mac, I get a seg fault. Okay? The P first pointer that I have is now pointing at some bit of memory that has already been deallocated. But wait a minute. If I have this Python code, I say same list, and I say A is L of 0, actually that function works fine. The reason is, in the caller code, I've taken an extra reference to that 0th element, and that keeps it alive long enough for that function to work, and I can print out that first element, even if I'm doing the wrong thing. And it can also work if you're making lists by composition here. So I say x is some value, and insert the list, and that function will work fine. Okay? It's because x keeps that the first object of the list alive long enough for you to print it. So this is our seg fault. Wait a moment. If I make the list of the numbers 1, 2, 3, this also works fine. Okay. The reason for this is in CPython, the integers -5 to 255 are forever. They never get forgotten. This is for efficiency reasons, but it does mean that you get lucky at this point. But imagine if that was your unit test, you were testing this function with the values 1, 2, 3, it works fine, you ship it into production, and then you give it the numbers 800, 801, 802, kaboom, you got a seg fault. So if this was a trading system in our code, and the FTSE went above 256, 255, suddenly we get a seg fault in production, which is not very happy when you've got $20 billion of client money floating around. What we got runtime errors we can only detect at runtime, and very data-dependent errors. This is not a shower that you want to get into. So let's go back to the problem. This is the function that we had, and the problem was calling this red function on the list while we already had references to items in the list. The fix is really simple. P first is a borrowed reference. Okay, it's not yours, it's someone else's, but they're letting you look at it. You want to register your, the fix is here. You need to register your interest in this thing by incrementing the reference count before you call that function. And once you lost interest in it, you let go of it by decrementing it. And all these seg fault cases that I've shown you will now be fixed. Okay? And as a flourish, you can set the pointer to null, because 100 lines later in the function, you might accidentally use it, and that's a good idea to catch that problem. So note that incrementing and decrementing references is really, really cheap. Seg faults in production are really, really expensive. So the last thing I want to show you is one coding pattern to make these dragons less far-breathing and more cuddly. And this is kind of like the requirements for this pattern. Okay, we want borrowed references to be incremented and decremented correctly. We want a single place for cleanup code, no early returns in any function, because that's a classic source of memory leaks. And we want exception consistency. So in C, when you want to raise an exception in Python, for the Python interpreter, you have to set an exception and return null from the function. Or, if you don't want to raise an exception, there must be no exception set and return a non-null. You have to do these things paired up together. So this is Pythonic. This is Python. We kind of write this stuff every day. It's kind of Pythonic Python. We've got a try block. We're going to do something crazy good. Okay. If we have any errors, we have an except block. Okay. And we might have a finally block as well for run-out code, like closing database connections and that kind of thing. And finally, we return the value. So it'd be kind of nice if we could write, this is Pythonic Python, it'd be kind of nice if we could write Pythonic C. Well, we can. Here's some C code that's almost exactly like the Python code. We have a try block, which is when we do our fabulous stuff. We have an except block for all of the cleanup code, and we have a finally block and a single pointer return. So I'll go through this in a bit more detail. So here's the function entry point. We declare any PyObject pointers that we need for the return value and for any kind of local temporary stuff. Declare them as null. We don't want some random previously stack allocated piece of junk in there. And we're going to go to the try block here. I would point out the last two lines are pretty irrelevant, but it gets us in the mood for writing Pythonic C. In the try block, it's going to look like something like this. We might put some defensive code in here, like asserting that no error has occurred, that no previous function call has set an error but forgotten to return null. We might assert that the argument that we're given is not null, so on like that. And that argument we're going to treat as a borrowed reference. We're going to increment it because we've been given it as an argument. It's not ours. We create some local object, object A somehow. If that fails, we're going to set an exception and then go to the except block. Carrying on with the try block, we're going to create a return value somehow. Okay. Again, if that fails, we set an exception, go to the except block. If that all succeeds, okay, we might want to have an assert to say that no error has been set up further up in the function, and we assert that the return value is non-null, okay, just as an extra check. And then we say go to finally, which will jump over the except block. The except block is where we handle all the failure. So we'll decrement any return value, if that's been allocated already. We'll assert that somewhere above us, someone has set an error properly, and we'll set the return value to null. This is pairing up the exception and the return value. And then we just drop through into the finally block because that's our point of exit. Okay, so if you remember, we have a local object here, object A. We want to decrement that because we no longer need it. We also had a borrowed reference, which was the argument. We must decrement that reference. And then finally, we return, and we're out. Okay, there's a bit more to this pattern than I've shown here, but for speed, I'll just show what I have. But all of this and more you can find on this GitHub, on my GitHub channel here. If you look under Python extension patterns, there's a whole load of tricks and tips, how to create debugging versions of Python, how to use Valgrind, so on like that. There are all sorts of useful stuff I found over the years that I couldn't find anywhere else. If you're writing C extensions, documentation's excellent. Use it. There's a really good tutorial to start you off, which gets you through writing all the boilerplate that you have to do for C extensions. The reference is huge and vast, but very consistent, I'd say, and the documentation for that is excellent. This is what you'll find on that GitHub link, okay, is just coding patterns and advice and tricks and tips. It's kind of mandatory to have some kind of war story to end up with. So I have an open source project which is basically reading proprietary binary files from the oil industry. These are kind of self-describing sequential format files. The problem with them is they can be quite large, and to read any part of the file, you have to read everything up to it, which is a bit painful. So the idea is to make them random access by creating an index of the file. The index is built up by a series of read and seek operations, so the read is about 1 or 2% of the file. So originally it was in Python, and it took about 10 to 100 milliseconds per megabyte to create an index. How fast can we go? Well, on the x-axis here, you have file size, logarithmic scale. It goes up to 100 megabytes. On the y-axis, you have the cost of creating this index in milliseconds per megabyte. And you can see the red crosses at the top. This is the original Python code. They tend to be around 100 milliseconds per megabyte. It took me about 3 days to rewrite this all in C. And now it's running 100 times faster, about 1 millisecond per megabyte. And there's some of the outliers, I don't know if you can see down below, are even 10 times faster than that. So 100 to maybe 1,000 times speed up over the original Python code. So in summary, one coding pattern for all your C code will keep the dragons cuddly. 2 things to avoid: allocation with no deallocation, and access after deallocation. 3 kinds of references to Python object pointers. Just remember the contract: new, it's yours; stolen, it's theirs; borrowed, you're sharing something that you don't own. Just let them know. And that's pretty much it. You can find there's my GitHub channel. My employer kindly flew me here. This is our Twitter feed. We're starting to open source quite a bit of our stuff, and it'll be announced here first. So if you'd like to follow us. And the unreadable block of code underneath, we are a financial organization, is basically my employer telling you, don't ask him anything about finance because he's rubbish with money anyway. But given that disclaimer, are there any questions? Oh, yeah, sorry, X DecRef will mean if you pass in a null pointer, nothing will happen. If you decref with a null pointer, bad things will happen.
I was curious if you've experimented with GCC's cleanup attributes, and if so, how that interacts with your coding strategy for these extensions.
GCC's cleanup attributes? No, I haven't.
Okay.
I'm afraid. Okay, thank you then. I'll look that up now. Sorry, the question was, should you always use the X DecRef? There's no harm in doing so.
I was just wondering, years ago I was looking at all this and was terrified. And then I discovered Python, and now I just let Python do all this for me. But you're not doing that. I'm just curious why.
Okay, yeah, sure. So we do use Python at work. In fact, on this GitHub channel, I've got another whole swathe of stuff about Python. So look me up. And also how you can use and abuse Python. For those of you who don't know, Python is basically a code generation. You write in a kind of pseudocode that looks a bit like Python. It'll generate C and compile that. It's a really good project. It's quite fabulous. The like of pandas use it a lot. And about 2 years ago, I fixed a bug in pandas because they were abusing Python, and you could segfault pandas in 2 lines, which is quite fun. But Python is really good, and it's a really quick way of getting C-like speed. And in fact, if you look at my GitHub thing, I show that Python, in some cases, can generate code that's faster than NumPy. One of the problems we perhaps have with Python is that it is a code generator, so your debug story has now got a lot more complicated. And sometimes the quality of code it generates can be a little bit variable, particularly when you move across versions. So we have had some experiences where things have suddenly slowed down. And again, if you look on my GitHub thing about Python, I can show you how you can create code that will run 100 times slower than it should do. So Python is a really, really good project, and we do use it. If you want really precise control and really the best performance ever, then we drop into C.
Thank you.
Okay, so the question was about CFFI. It's on my to-do list, really, so I'm probably not the best person to answer that question. Sorry, someone at the mic.
Are there any other higher level tools that you've explored that, for example, things that generate frameworks for you so that then you can write C, or things that do faster code at higher levels?
Yeah, well, Python is probably the one that
Right.
would choose. That's the one I got most experience with, so it's the one I can speak most for. But there's some other ones as well around. There's quite a few coming out. There's quite a nice project I looked at, and I just only just last week, which I think it's called PyC11 or something like that. And basically they use C++11 to wrap all of these reference counting things up. And that looks like a really cool project.
Okay, thanks.
Oh, is it PyBind, is it? Yeah, that's the one. Okay, PyBind. No, shout out for PyBind. It looks really good like that. Anyone else? We're done. Thank you very much.